Welcome to this explainer. Today we're tackling a massive headache that literally every competitive programmer hits at some point: integer overflow. We're going to figure out exactly how modular arithmetic and GCD, greatest common divisor, can step in to save your code from completely failing those massive, nasty test cases.
Okay, let's just glance at our roadmap for today. We'll start with why modulo matters, then cover modulo rules and preventing overflow, followed by the negative modulo trap. After that, we'll shift gears into mastering the GCD, array GCD in complexity, and finally wrap up with cryptography and a quick review. All right, let's jump right into section 1, why modulo matters. So, why do we even need modular arithmetic in programming? Well, when our algorithms start crunching really large numbers, we have to ask ourselves, how on earth do we keep these values manageable? I mean, think about your typical 32-bit integer. It has a hard physical ceiling in your computer's memory. If your algorithm calculates combinations, factorials, or just massive power functions, you will blast right through that ceiling in mere milliseconds. That causes integer overflow. Your data gets corrupted, and your program either crashes or just spits out total garbage. So, how do we contain the uncontainable? We do it by literally changing the rules of the playground. It's all about this idea of numbers wrapping around, kind of like a clock. Think about a standard 12-hour wall clock. If it's 10 o'clock right now and you add 5 hours, you don't say it's 15 o'clock, right? The numbers wrap around, and you say it's 3 o'clock. That right there is modular arithmetic, with a modulus of 12. In programming, we set a specific modulus, usually some giant prime number like 10 to the 9th plus 7, and enforce this exact wraparound system so our intermediate variables never, ever exceed our memory limits. Moving right along to section 2, modulo rules and preventing overflow. Now look at this. This is basically your ultimate cheat sheet for addition, multiplication, and exponentiation modulo. Notice a pattern here? We aren't just calculating A times B and then slapping a mod on the final result. No way. If we did that, the intermediate step might already trigger an overflow. Instead, you apply the mod to A. You apply it to B, you do your math, and then you mod the whole thing again. This mathematical property is absolutely your best friend. It guarantees that at absolutely no point in your code does any single variable get bigger than the modulus itself. To put that into perspective, if you try to calculate a power function directly without applying these modulus rules at every single step, your machine is going to run out of bits instantly. But if you inject the mod operator inside the while or for loop of your exponentiation function, you're continuously squashing that number down at every single iteration. Instead of letting a to the power of n explode, you keep computing a smaller, mathematically equivalent value. It stays perfectly safe and contained. A real game changer. Okay, let's look at section 3, the negative modulo trap. So this is a massive gotcha that interviewers absolutely love to test you on. It's where pure math collides with language compilers. In pure math, a modulo operation always gives you a positive remainder. But thanks to language-specific quirks in Java and C++, negative dividends can actually produce negative modulo results. For example, negative 5 mod 3 might hand you a negative 2. If you try to use that negative number to access an array index, bam, your program crashes instantly. The fix is super simple but absolutely vital. Instead of just writing a mod b, the classic interview trick in C++ or Java is to write, actually, let me spell it out. Open parentheses, a mod b plus b, close parentheses, mod b. This ensures that even if you get a negative 2, adding the 3 brings it up to a positive 1, and the final mod keeps it totally safe. Boom, you're back in the positive realm. All right, shifting gears to section 4, mastering the GCD. So what about the greatest common divisor, or GCD? This is honestly the perfect mathematical companion to modular arithmetic. It's the largest integer that cleanly divides a set of numbers without any remainders. We use it all the time for simplifying fractions, finding sequence patterns, and even in advanced cryptography. But here's the thing. Trying to find the GCD by brute force, like checking every single integer from 1 up to n, is painfully slow. We absolutely need a faster way. To get that faster way, keep these 3 foundational properties in mind: reflection, identity, and associativity. These are the exact building blocks we use to write the code. Reflection basically says the order doesn't matter. Identity is super clean. If one number is 0, the GCD is simply the other number. So the GCD of 0 and 5, it's just 5. And associativity, this one is huge, means we can take a massive sequence of numbers and just process them in bite-sized pairs. And here is where it all comes together, the Euclidean algorithm. This is where modular arithmetic and GCD join forces. Instead of just guessing divisors, we say the GCD of A and B is the exact same as the GCD of B and A mod B. Let's do a quick mental dry run. Let's say we want the GCD of 10 and 4. We shift that to the GCD of 4 and 10 mod 4, which is 2. So now we need the GCD of 4 and 2. We shift again to the GCD of 2 and 4 mod 2, which is 0. And once B is 0, thanks to that identity property we just talked about, our answer is A, which is 2. You just loop this one simple line of code. It is stunningly elegant and literally lightning fast. Which brings us to Section 5, Array, GCD, and Complexity. So how do we actually scale this math to process an entire array of data? Well, it works entirely because of that associativity property we just looked at. You just calculate the GCD of index 0 and 1. Then you take that answer and find its GCD with index 2. Take that answer and pair it with index 3. You just ripple or cascade that result iteratively down the rest of the array in one single clean pass. When you implement this array approach, your time complexity hits big O of n times the log of the maximum number in the array. Let's break down why that's so cool. The n just comes from iterating through your array of n elements, but the log of max underscore number comes from the Euclidean algorithm itself. Because the modulo operator effectively halves the problem space in at most 2 steps, the numbers shrink logarithmically. Interviewers love seeing this because it means even if your array is packed with astronomically huge integers, your algorithm will solve it in near linear time. No sweat. And finally, Section 6, Cryptography and our final review. Let's tie all this theory to its most vital real-world application. Why does the modern digital world desperately need modular arithmetic? Well, cryptography. It relies entirely on these modular rules to manipulate data into massive numbers and secure it over networks. Algorithms like RSA depend on how hard it is to factor giant numbers. To encrypt a message, we perform exponentiation on massive primes. Honestly, if we didn't use the modular exponentiation rules we discussed today, no computer on Earth would have the memory to calculate the encrypted cipher. Modulo creates the contained mathematical environment that literally protects all of our digital transactions. Okay, let's do a super quick recap before your next coding interview. Number 1, always use mod to prevent overflow and apply it at the intermediate steps, not just at the end. Watch out for the Java and C++ negative trap. Remember to add the modulus back in. Use the Euclidean algorithm to find GCDs gracefully, and remember how perfectly that scales logarithmically across arrays. So, knowing how insanely fast data types can overflow, how will you use modular arithmetic to ensure your next algorithm scales flawlessly? As you head into your programming challenges, really think about these boundaries. Are you just letting your variables grow unchecked, crossing your fingers they don't overflow? Or are you actively engineering the boundaries of your data? Take these formulas, memorize that Euclidean trick, and go write some unbreakable code.